questions?
Okay, let's get started here. So project number 3 is due Tuesday, October 18th. We will probably talk about it a little bit today until we're good to have out, ready to go. Are there any questions before we get going here? Okay, we were talking about semi-parametric models and how Bootstrap can take advantage of the semi-parametric part of it. Specifically, we were looking at an example with symmetric distributions. Where in order to induce, we have to induce symmetry into our EDF in order to take advantage of the symmetric property. Turn off some of my spell check in here. And to do that, we said, well, why don't we take our EDF, which we take resamples from, to consist of not just y1 through yn like usual, but also 2 mu hat minus y1 through 2 mu hat minus yn, where mu hat's the median. And what this does, it allows for the f hat to be symmetric. So that's where we left off last time. What we're going to do is just a simple numerical example to help illustrate that indeed that we do get a symmetric f hat, and to show how one would actually go about using the Bootstrap. There's one small thing that you have to be careful about. So what I've done is simulate data from a non-symmetric distribution, simply an exponential. So I set a seed. Let's say I have a sample size of 20. Let mu be 14, and use the REXP function to get my non-symmetric data. So histogram of y, you can see obviously it's not symmetric. But what I need to do is again take my f hat to be this, I guess, transformed set of data. So to transform it, simply just create a vector that has y in it, and also 2 times the median of y minus y. And so now this is what it looks like. Now the thing that you have to be careful about is that, what's my sample size? My sample size is 20, but I actually have 40 elements in y.sim. So when you actually take your resamples, you need to make sure that you only take resamples of size 20. And let's see how I do that coming up. So just to verify that indeed that this little transformation allows us to work with symmetric distribution, how about we look at some plots? So first of all, a histogram. How about we put a normal distribution plot upon it? And also I'm just simply going to use a density estimator. I'm not going to get into density estimation too much. But it just provides a simple way to estimate a density without specifying a particular distribution, so to speak. And so the red here is the normal distribution, the blue is the density estimator, obviously, with the shape of the histogram. Maybe this isn't the best, but you can see that indeed it is symmetric. I think what's a little bit better is to look at a plot of the EDF of my y.sim. Here we go. First of all, why did I draw a line here at 0.5, do you think?
That's where the line of symmetry should be.
Well, basically what's above here should be a mirror image of what's below here if I have a symmetric distribution. Indeed, that's what we do see. So I'm taking resamples then basically from this f hat right here. So let's talk about how the resamples are taken. I construct my usual calc.t function that I can use with the boot function. I'm going to pass in my usual data and also the indices of the items to take from my resample. I also going to pass in n, my sample size. my true sample size. D gets data I, like usual. And then, just so that I have a statistic that I can calculate here, this particular problem in the book, or example in the book, doesn't actually deal with data. I'm just showing you some data so that you can get a better feel for it. And so there's not a particular statistic mentioned in the book. So just to make things simple, how we look at the mean. So I say mean D, and notice what I do here. I only take the first n items. So that's how I make sure that I'm actually taking a sample size of 20, a resample size of 20 versus a resample size of 4. I guess there's probably maybe other ways that you could do that as well. It's just this is the approach that I took. So let's just try it out on the data. And indeed, if I do mean of y.sim, oops. Here. Get the same thing. I really wish, I don't know if do I ever block this so you can't see actually? So I always feel like I'm blocking, so I try to always remember to move this over. Oops.
Are the first 20 values of y.sim also y, so you can do mean of y?
Yeah. So then to do the bootstrap, very simply, how we normally would do it, I just pass in an additional argument into cap.t. And remember, you do have that, I think we've seen this before, you do have that option that you can put arguments that are not in boot, because the ... Put arguments that are not actually specified in boot, put it in there so that they can be passed along to some other function and ends up being called. And so if I run this and then do a histogram, notice the histogram of the T stars. It kind of looks symmetric. Notice the QQ plot, it looks symmetric. Normality might be questionable since we do have those deviations on the tails. Okay. Any questions? So then that concludes this particular particular section on with a semi-parametric model. And as you can probably imagine that, applications of the Bootstrap is kind of specialized to the particular assumptions that you're making. Obviously, the symmetry assumption was quite different from what we did originally at the very, very beginning of this section, where we specified like a linear model without a normality constraint. Okay, page 323. Okay. So in Chapter 3, there's a lot of sections that talk about specific applications of the Bootstrap to particular statistical methods. If we have not seen those statistical methods before, it's then hard to understand how the Bootstrap is going to be used for that particular statistical method. So for example, how many of you have had a course in survival analysis? No one's taken a survival analysis course? It's a fun course. Actually, I think that's our newest actual numbered course in our department. I think it's Stat 874, I believe. Or maybe 876. Might be 876. I think it just recently got a course number. Julia Sulikova teaches. So obviously, if I were to do the section on survival analysis, I would need to teach you survival analysis. That would take some time, obviously, because we have a whole course on it. And so then I can actually get to the Bootstrap. And so you might remember me mentioning the very first day of class that this particular course can be difficult to teach because The Bootstrap's used in many, many different places, and the book talks about these many, many different places. But it's hard for me to find particular places that all of you have had before, so that I can actually discuss it in detail. So because of this, I am going to skip sections 3.4 to 3.8 in the book. But these are good sections. And so I just want to briefly talk about them. And perhaps if in the future you come across a place where you've taken a survival analysis course, or you have some survival analysis stuff, let's say in your dissertation, you know where to look. You know the Bootstrap can be used in these situations. So, real briefly, section 3.4, smooth estimates of F. Now, F hat EDF is obviously a discrete distribution. And we've seen how the discreteness plays a role in some plots that we've looked at too. And there are times where that discreteness, you don't want it. Just simply. So maybe it would be nice if you could somehow smooth out that distribution so it's not as discrete. And so this is what you can do. Take your resampled value, and this is the book's notation, so if you don't like it, blame the book. Take your resampled value that we normally would call y star sub j to be the following. This little notation here basically just means how you would normally take your resample. So just simply take your y from the original data, and what this notation is basically saying is the indice here is basically what you're resampling. And this kind of matches what we do with the boot function. With that, our calc.t, we pass in I. So we're actually just resampling indices and then using that to determine which items are actually in our resample. So that's what this is basically saying. Just do your resampling like you would normally, but add to it h plus epsilon sub j, where epsilon sub j is simply sampled from some continuous symmetric distribution, usually just like a parametric, maybe a normal. Sample from that, and then multiply it by h, which is often referred to in many other applications, a smoothing parameter. So notice if h is equal to 0, you get your regular resample from the EDF. If h is greater than 0, then you can see how we're going to have a little bit of a perturbing, you could say, of our normal yj stars. And this is going to help smooth out then what the actual resample ends up being, and of course then the corresponding distribution. This is called the smooth bootstrap. Section 3.5, censoring. Well, censoring appears when you're dealing with survival analysis. It also occurs with respect to reliability analysis. Basically, survival analysis is often dealing with, let's say, survival times. Reliability analysis, in particular, we've actually seen one example, kind of, with the air conditioning data. How reliable is the air conditioner on an airplane? That's reliability analysis. And so, often, of course, in survival analysis and also reliability analysis are actually interconnected. To be honest, I think this is one of my more favorite areas of statistics, even though I don't do research in it. It was actually between survival analysis, reliability analysis, and categorical data analysis for my dissertation. I chose categorical data analysis. Anyway, though, so censoring. Does anyone know what censoring is without reading what's on the screen? Anybody heard of censoring? Do you see it like in 971 at all? Where did you hear about it?
It's like that in sports stats.
Oh, how does that how does censoring appear in split statistics?
This field goal kicking.
Really?
Yeah.
What's
Well, it was place kicking kind of in general because they were kind of censored at wherever the place kick for the point after. That's kind of, there's not anything shorter than that kicked ever. And so.
Yeah, I guess on the surface I wouldn't call it censoring, but
Someone in consulting had censored data too.
Okay. We can maybe discuss it after class since I like field goal kicking. I'm taking my 75 class.
It was a couple years ago now. I don't remember the details.
Anyway, censoring. Censoring is really interesting in that you have an observation, but you don't know everything about it that you would, let's say, normally. So, normally we observe data like the number 5, the number 8, the number 10, but you might not know exactly what the actual observation is in a censoring situation. Perhaps that's not the best explanation, but let's talk about it in this context. Clinical trials. Definitely censoring often appears in these kinds of settings. So let's say that there's just some kind of clinical trial on a new drug that's meant to prolong persistence. And, clinical trials can't run forever. And suppose that there's a cap of 36 months. But, maybe a person who's in the clinical trial has not, let's say, died before the end of it. Well, what do? Do you say that they're, if you're measuring, let's say, suppose, I know I'm using T here in a different way that we have in this class, but let's say T is survival time. And if a person's in the clinical trial all 36 months, he has not died, you can't just say that T is 36 for them. You can't, because they're still there. So this is an example of a censored observation. We have information up to 36 months, and then we know that the person is still living, but we don't know how long. So their actual observation is somewhere greater than 36. And in a data set, often you would denote this time as 36 plus. Another example when censoring occurs is that suppose that a person's in the study for 24 months without dying and decides to pull out. They decide, okay, I'm not going to take this drug anymore. Well, then we know that their survival time is greater than 24, but we don't know exactly what it is above 24, so this is often referred to as 24 plus. You can actually, with censored data, actually have, so this is actually called right censored data, because you're chopping it off on the right side. You can actually have left censored data. I know that happens in astronomy. I don't know how, but I know it happens. You can actually, I think you can actually have something like left and right censored together. I don't know how that happens, to be honest. But typically, right censored data is the one that we more deal with. And so what we can do in this kind of a situation is define y to be the minimum of y0 in C, where y0 is some true response time, so true survival time that you may or may not know, and C is the sensory time. And what you actually observe is this y, the minimum of the true survival time and the sensory time. So, anyways, if some of you are looking for other classes to take, I do recommend a survival analysis course because it is widely applicable, but it really helps you understand what a likelihood function represents. Because now, not only do you have to worry about, normally how we write a likelihood function, let's say like this, but now, if you have people that have lived longer than what you've observed due to censoring, then the survival function, then the likelihood function becomes something like this. where notice, I didn't write it very well. So you have the product of, let's say, f of xi, which would be the people that we do observe their, let's say, survival time, times times the product of 1 minus the CDF. That 1 minus the CDF says, okay, you have, what is a CDF? The probability that x is less than x, right? So if you know that they have survived longer than time x, then 1 minus that CDF is what gives that to you. And so you write your likelihood function like this instead. Anyway, that's getting more into than we want to. But so section 3.5 talks about survival analysis, how to actually estimate. This actually has a special name called a survival function. How to estimate a survival function, and then incorporate the Bootstrap. Section 3.6 deals with missing data. It's a topic that I don't know a whole lot about, to be honest, but I would love to know more about it. So often we deal with missing observations. Maybe if you're, let's say, observing x1, x2, x3 on individuals, suppose that one particular individual doesn't have x2. What does often statistical procedure? What do statistical software often do when you want to fit a model to data like this? Throw it out. Yeah. So even though you know x1, x3, often by default, statistical procedures, let's say like proc, GenMod and SAS, or even GLM function R, throw those observations out. Well, it would be nice if you don't have to throw that, because you're throwing out information, especially if this is not missing, necessarily at random. And so there are particular things that you can do called imputation that allows you to take care of that. And lastly, section 3.7, finite population sampling. In so many things that we do in statistics, we assume that we have actually an infinite size population. But what happens if you do have a finite population size? How do you take that into account? And, of course, like Stat 804, our survey sampling class, we'll talk about how to do that. But how does then the Bootstrap then work in this kind of a setting? Well, that's what the section 3.7 talks about. In particular, what makes it difficult, and you can't just apply the Bootstrap normally like how we normally would do it, is what makes it difficult is that let's say that you're interested in the sample mean. Normally, the sample mean itself, of course, has a variance of sigma squared divided by n, but in your very first stat course, you typically learn about if you do have a finite population size, you have to worry about that finite population correction factor, where capital N is the population size. That is actually the variance of the sample mean. So resampling, though, like how we normally have done, unfortunately doesn't allow you to take into account this extra factor. So some kind of adjustments need to be made. There's been a variety of adjustments. And of course, people come up with names. There's a mirror match bootstrap. There's a superpopulation bootstrap as well that allows you to take into account this extra variability. And this has been extended to complex survey sampling situations as well. And last, now this is last, hierarchical data. A lot of you have experience with this kind of setting where you have, let's say, multiple sources of variation in experiment. A classic example is the split plot experiment. So if you're interested in this, here are some recent papers on that area. Okay. Any questions? So it takes us to section 3.0. Bootstrapping the bootstrap. So guess what? We're going to do the double bootstrap. We talked about that a little bit in Chapter 2. If you remember from Chapter 2, it can get a little bit confusing. Just because you are bootstrapping something, you're already bootstrapped. And in fact, you may face a little bit of confusion here. But please make sure to speak up and ask questions. We're going to talk about the double bootstrap in two contexts. First, how to deal with a bias correction of a statistic. We're actually going to be finding the bias of the bias. And then we're going to talk about situations with respect to estimating the variance and how a variance itself can be a function of your parameter of interest, which can cause problems. If you remember when we were talking about variance stabilizing transformations, we're going to look at ways that you can use the bootstrap to help figure out what kind of transformation to use. If you can find that transformation, then that's going to mean then the statistic that you're working with bootstrap is going to be better. Okay, so section 3.9.1, bias correction of bootstrap calculations. Be careful with the book's notation, as always. So, we've seen before expected by a T star given F hat is equivalently expressed as expected by star of T star. Book goes back and forth. In this particular section, this is the only place where I found this in the book, they decided to add a star to that expected by a T star given F hat. I don't know why they did. I think it's a typo. I don't think it should be there, but that's what they do. I think they're trying to overemphasize it. Okay, so the true bias, and we've discussed a little bit of this before, but we're going to go into a little bit more detail. The true bias was denoted in Chapter 2 by beta. Again, you can think of that as a statistical function. It's called B of F. And that's simply expected by a T given F minus T of F, or in other words, expected by T minus F. We look at how to estimate this bias. So the bootstrap estimate of the bias, which was denoted by B, results from simply putting a hat on top of F. In other words, expected by a T star given F hat minus T of F hat, or expected by star T star minus T. That's the bootstrap estimator for the bias. Now this B is a statistic. Now it's going to vary from sample to sample to sample, because notice what's in here. We have this T. It is a statistic. Is B going to be exactly equal to beta? No. So, as I say here, it's natural to wonder about its statistical properties then. How good is this estimator of the bias? Well, how do we measure good? Well, we find the bias of the statistic, so we're going to find the bias of the bias. So, quantities of interest then. I've obviously done this section a number of times, so what you're going to notice here is that there's going to be a lot of reviews throughout this section to help emphasize what we're doing here in understanding the notation. So you're going to hear me repeat some stuff a few times, but I have found that helps. The bias of B. How about we just call it gamma? It's the book's notation. It's a statistical function too, C of F. So in other words, what's the bias of B? Expected value of B minus the true bias. In other words, expected value of B minus beta, or expected value of B minus expected value of T minus theta. How would we estimate this in the bootstrap context? How about we call the estimate C? Well, now you put stars in places where we didn't have stars before. Parameters now become statistics. So, expected value star of B star minus expected value star T star minus T, which corresponds to theta. So you take the expected value of B star with respect to F hat minus the bootstrap estimate of bias. So in other words, expected value star of B star minus B. That looks simple enough. But you got to remember, though, that B already came about through the bootstrap. So what's the expected value star of B star? Here we go. B itself is already a bootstrap estimate. So that means we're actually going to have to use a second bootstrap. In other words, a double bootstrap. Or you can think of it as a second layer of bootstrapping. So B star then is expected value star star of T star star minus T star. Let's take a look at this. B itself, again, was a bootstrap estimate. So B star itself is a bootstrap estimate of a bootstrap estimate. In other words, expected value star star, T star star minus T. Okay. So what is T star star in words? If someone phrase it in words what T star star means. We've actually done this before. I think it's good for a review. So it's your statistic of interest calculated on a resample of a resample. So it's your statistic of interest calculated on a resample that comes from a resample. I don't know, depending upon how you want to word it. I mean, sometimes people like to say T is calculated on the resample. Split screen action here. So let's talk about C then. So this is the bootstrap estimate of the bias of B. In other words, it's an estimate of the bias of the bias. So C is expected value star, B star minus B. We're going to go through this slowly. So let's say that's step 1. Step 2, let's put in what B actually is. Expected value star, T star minus T. Step 3, let's replace B star with what it is. Expected value star star, T star star, minus T star. Step 4, let's work with expectations like what we do normally. So I can bring this expectation inside there. So expected value star of the expected value star star of T star star minus expected value star T star minus expected value T star plus T. So I combine that in step 5. I simply combine these two. So that's C. Again, an estimate of the bias of the bias. Here's one of my places of review. Again, T star comes about through sampling from F hat. T star star comes about through resampling from F hat star, which is the estimated distribution for the resample Y1 star through Yn star. Now, you can think of, perhaps, if you don't, this is sometimes confusing, but so if you don't want to be confused, don't listen here. You can think of this T star star then as a statistical function a statistical function, scribbled out, T of F hat star star. Again, think about what that means. this is the EDF of a resample from a resample. Or you can think of it as EDF of a re-resample, if we were going to use that terminology instead. So, great. We got this thing called B. We got this thing called C. B is the bootstrap estimate of the bias. C is the estimate of the bias of the bias. It's a bootstrap estimate of the bias of the bias. So how can we use this information? This goes back to what we first saw at the end of the Chapter 2, Part 1 notes. But then we're going to add some stuff to it. So let's just say, for some statistic out there, our bias is known to be 3. And T is an estimator that we're going to use for theta. And it happens to be biased. So this T has a bias of 3. So that means then that the expected value of T minus theta is equal to 3. If you knew that, then it would make sense to, well, why don't you just simply use a different statistic that's adjusted for this 3? In other words, use T minus 3 as your new estimator, because the expected value of T minus 3 minus theta gives you an unbiased estimator. So T minus 3 is unbiased. So then what that means then is that we are saying, let's let our estimator be T minus beta, or you can say T sub BC. Not for builder crisp, but for bias corrected. It's a bias corrected estimator of theta. The problem is we don't ever know beta in the real world. Actually, we will know beta coming up. We will not typically know beta. So this is where then the bootstrap comes in. We let B then be the estimator of this bias using the bootstrap. And then we take then our bias corrected statistic to be T minus B instead. So instead of having a beta there, we put a B. Makes sense. Makes sense. In actual application then, you would observe a T and you would observe a particular bias as well. Okay, so that was introduced in Chapter 2. Now the new stuff then in Chapter 3 involves the double bootstrap. C is an estimate of bias of B, because of course B is not going to be a perfect estimate of beta. So then the adjusted estimator of the bias of T then would be B minus C, using the same stuff that I just did above. So how about we call this adjusted estimate of the bias B sub ADJ, adjusted. Then, instead of using B in our calculation here to come up with a bias corrected statistic, how about we use B adjusted instead and take that as our estimator. How's everything so far? Okay. So, another review. T is not a perfect estimator for theta. T minus beta, generally speaking, is to be a better estimator for theta, because it takes into account the possible bias of T. Of course, B is not a perfect estimator of beta. So, how about we take B adjust, which is B minus C, as a better estimator for beta, since it takes into account the possible bias of B. Then we use B adjusts instead of B to produce our actual statistic of interest, T minus B adjust. This should be better. Let's take a look at an interesting example. I like this example. This comes from the book. This deals with the sample variance. Once again, we have this bias sample variance. Well, in this particular case, we can actually have a nice little closed form expression for what the bias would be of this sample variance. So, the true bias, beta, is expected value of T minus sigma squared. That's the variance of y. Now, remember that if I take let's just rewrite that. Maybe it's needed, but might as well. If I take this quantity times 1, n minus 1 divided by n minus 1, and let's say that I move this underneath and move this outside, this means then I have t this means I have, let's call it s squared, our normal unbiased variance, times n minus 1 over n. And of course, we know the expected value of s squared is sigma squared, and so that's how I get this part right there. Just make sure that that was clear. Do a little algebra, and you get negative sigma squared divided by n. That is the bias of this estimator of the variance. Well, what does the Bootstrap do then to estimate the bias? Well, it tries to estimate beta with b. So we take the expected value star t star minus t. Now I'm going to pull out a result that actually is given in the book. This is number 3 on page 61. Sometimes I give this as actual homework problem. I don't think I did this time. Did I get this? Sorry, I don't remember now off the top of my head. For project or homework. Anyway, number 3 on page 61 of the book shows, not too bad, expected value star t star is equal to n minus 1 over n times t. Nice little closed form expression. So, when I substitute this in here, I subtract t, again do some algebra, I get negative t divided by n is my Bootstrap estimator for the bias. I have a nice little closed form expression. Well, what's the bias of b? Because we know that negative t divided by n is not going to be a perfect estimate of negative sigma squared divided by n. It's not going to be a perfect estimate. So what is then the bias then of b? I can find that. Expected value of b minus beta. So I'll just simply put in what b is, put in what beta is. Just do some expectations, do some algebra, see the details on your own, and I get sigma squared divided by n squared. Okay. So that's the bias. Well, how would then the Bootstrap estimate the bias of B? Well, here's how it goes. So this is using then the expression that's on page 329. We take C to be the expected value star star, T star star, minus 2 times expected value star, T star plus T. Okay. Using that result that was that's in number 3 on page 61, you can show that this expected value star star, T star star, is n minus 1 over n times T star. So I can plug that in there. We know what the expected value star T star is based on that result as well. Then I can still apply that result from expected value star T star one more time, do some algebra, make it T divided by n squared. That's my C. So, once I have that then, I would want to say, well, let's get an adjusted estimate of this bias. So I take B minus C. Negative T divided by n minus T divided by n squared. That's my B adjust. So the double Bootstrap bias corrected estimate of sigma squared then, T adjust, is T minus B adjust, or T minus what I had for B adjust. We just look at the end result. It's this. Okay. happening to this estimator? Is it going up or is it going down? It's going up. After the adjustment, maybe I need to phrase it correctly. The adjusted estimator here, is that higher or lower than what the original value t was? It's higher, right? Okay. Well, why would we want that to happen? Again, take a look at the formula for t. And also, take a look at the formula for our normal sample variance that we denote by s squared. Which is larger, s squared or t? S squared is. So divided by a smaller value out front. So it makes sense then for an adjusted value of our original statistic t to be higher. Because we know that the unbiased estimate of sigma squared is actually higher. So that makes sense. But let's look at it another way. This is the way the book does it. Is this an improvement? Is this statistic actually an improvement? Okay. Compared to if we just did a bias-corrected statistic. So we didn't use a double bootstrap. We used the stuff that was at on section 2.4. Well, so here's my bias. Negative sigma squared divided by n. Lost my train of thought. So the estimate is beta, and we have a closed form expression of it that's based upon a random variable. So that closed form expression is negative t divided by n. So I could actually take an expected value of that. If you do that, you get beta times 1 minus ren. I can do exactly the same thing with b adjust. We found that to be a function of a random variable, or statistic t. Again, take the expected value of it just with respect to f itself. And we get beta times 1 minus 1 over n squared. So, which of these estimated, b or b adjust, is closer to beta? B adjust. Thus, that's why it makes sense to do a double bootstrap. Could you do a triple bootstrap? Could you? Yeah. Do you think you're going to get a better estimator?
You can get n
Yeah.
minus 3 instead
Yeah.
of minus 2.
You're going to get it better. So you can do a quadruple. You can do, keep on going as long as you want, to some respect. You can continue to get a better estimator. Of course, then it comes to a point of, well, is it really worthwhile to go, that many levels in terms of bootstrap? So I don't think I've ever seen anybody do anything higher than a double bootstrap. But you can see that it could help. So there's a double bootstrap. Now, what we've done so far in this little subsection is that we have actually been able to find these expected value stars. At least I presented them to you, and then in this simple variance problem, we could actually find them. But in an actual application, most of the time, you're not going to actually be able to come up with a closed form expression for it. So you're going to have to use Monte Carlo simulation. In other words, you're going to have to actually formally take the resamplings to come up with estimates of these expected values. So here's how you can do it. This is an algorithm that's given in the book, on page 334 of my notes. So first of all, how about we just estimate B itself? We've actually done this before, but we can review it. So B is, again, expected value star T star minus T. How do we get that? We take our resamples from F hat, and you can think of it this way, then we obtain our different EDFs for each one for each resample. We calculate T star for every single resample. Then our observed value of B, little b, is, of course, then the average of these T stars minus T. And, of course, again, we do all large numbers. This should go to this, as long as we take R large number. Okay. Now, this is the new part. We want to calculate this C. So now we have these R resamples. What we're going to do is within each of the resamples take M more resamples. Again, from within a resample. So M resamples taken from each of the F hat stars, some R's. Then, for each of these, again, resamples, we call them, we're going to calculate T star, and at least up here, and I think even in the notes sometimes it's hard to read this. This is a T star star with a subscript R and an M. Maybe I should put just a comma between them to separate. So this helps designate which resample this T star star is coming from. Then what is C? Well, notice what we are doing here with these expected values. To do this first expected value here, we need to calculate basically this is not very mathematical what I just did there. We need to calculate then the average for the Rth resample of these T star star RMs. Then to get the outer expectation, and that's where we average over the R resamples themselves. We take then -2 times then, as you would expect for expected value star T star, the average of the T stars, and then plus T. Is everyone clear on how to get this C? Any questions? So, then the adjusted estimator of the bias of T would be B adjusts, little b minus little c. The double bootstrap bias corrected estimator of theta, called T adjusts, is T minus B adjusts. And again, here you can see that we are taking R resamples plus R times M more resamples at the second layer of the bootstrap. So a lot of resamples. Okay, so page 335. How would you program this into R? Let's talk about how to do this. So you're going to run the boot function. So how about we put some code? We're going to write pseudocode. So we're going to put the boot function here. In the boot function, you need to specify the number of resamples. How about we just say R? You're going to need a second. Make sure I get my syntax correct. Obviously, you're going to have your data, and you're going to have your statistic. How about we call it calc T? And you might pass in some other stuff. So, with the boot function is going to call a function called calc.t. We're going to have data, I, maybe some other stuff. What do you think is going to be the last thing in calc.t? You're going to calculate, you're going to pass back the statistic. Inside of here, though, you need to somehow take those M resamples, right? So you're going to have a call to boot. oops, let me make sure. Sorry, let me erase that a little bit. Let's say D gets data I. You're going to have to call the boot function data equal D statistic. What should we call the function? Well, calc.t2. Number of resamples, M. Maybe you're going to pass in some other stuff. So then we have to write calc.t2. Data I. Obviously, D gets data I. And you're going to need to somehow calculate your statistic. Which, catch on. Okay. So, what's going to be passed back to this? Of course, I probably didn't say my results. You're going to have your T star RMs. And if you notice, we're going to have to calculate, based on page 334, we're going to have to calculate the mean of those T star RMs. And so you're going to need something with respect to that there. So, I don't want to tell you exactly how to do it, because I guess we're at a point of the semester that I hope that you can do this stuff without me necessarily giving you exactly all the code. But what I want to do is set up some pseudocode here to help you out for project number 3. So we'll talk about project number 3. I guess I decided just to continue with the same theme that we've had in Project 1 and 2 by looking at some stuff that was originally in Castellenberger's book. And let's let T be the normal unbiased estimator for variance, and T bias is going to be now the usual bias estimate that we have been working with too. And we're going to use the same data that we used in project number 1, which corresponds to example 10.1.22 of the book, of Castellenberger, excuse me. And just to begin with here, just to make sure you get the right answer, we're working with the right data, calculate T and T bias. One of the easiest problems of the whole semester. And part B then, using actual resamples. Now remember, we just went through all the deprivations without the resamples. What I want you to do here is for this data set, with actual resamples, find the bootstrap estimate of the bias for both T and T bias. And find the corresponding corrected statistic, observed values. Let me just emphasize. Observed. We weren't talking about observed values at all in that example that was in the notes involving the variance. But this is, we're just doing one sample itself. We're looking at an observed corrected statistic value. Now compare your bias estimate and corrected statistics to what we know are the actual values. Remember, Castellenberger say sigma squared is equal to 4. Make a comparison. Just so that everyone gets the same answer, use a particular seed number with the boot function, use R equal 1,999. Part C. Now using actual resamples again, find the bootstrap estimate for the bias of the bias. So this is now where really the new stuff in section 3.9 comes in. compare these estimates to what you think should be, what are the true values. Use m equal 500. Notice you are using the original resamples. That was in Part B. Part D. So after I was writing this up in the answer key, I was kind of surprised at what at first, for like 30 seconds. I was surprised at first with what I was having happen. And that is, you may be surprised that the corrected statistics are not closer to sigma squared. The corrected estimates, again, these are observed values, are not closer to sigma squared. Why is this not a cause for concern? Describe how one could actually evaluate if a similar problem occurs for other, let's say, samples. Just gets into the idea of the difference between the statistic rates in terms of the random variable versus the observed value, without going into too much detail. Part E involves section 3.10. And we won't get to section 3.2 until next class. So you pretty much now are set up to go with project number 3. Just this number 2 emails left for us to discuss, which is really not much. I just kind of threw it in there because I wanted to give you some experience with section 3.10 stuff. Any questions? Okay, let's go back to the notes. So again, section 3.9 is basically divided into 2 different parts. One is the bias correction, and the next part is talking about variation properties of T. In other words, this variance of T, if it's a function of your parameter of interest theta, that can cause us problems. And we discussed that a little bit back in section 2.5. That was a section where we talked about a variance stabilizing transformation and how then that can also help us then in inference procedures. Because now there's one less thing that you have to worry about estimating. If you have some kind of transformation of T that allows then the variance itself to no longer be a function of theta. Okay. In the perfect statistical world, how could we check if the variance was a function of theta? Well, in a parametric setting, you'd have variance of T is equal to, if you see a theta in there, you know if it's a function of theta or not. But suppose we cannot simply look at a closed form function for the variance. What can we do? Well, we could, let's say, for a particular value of theta, suppose it's on a plot here, suppose it's a low value of theta, simulate some samples of that, and then from that, calculate a variance. And suppose we get it right there. Suppose for another value of theta, let's say it falls here, we also get a variance. And we can keep on doing that for a whole bunch of different values of theta. And if what we see here is that generally speaking, the variance doesn't change a whole lot, then that says that our variance of T is not a function of theta. If, however, we see a plot that looks like this, where we see some kind of trend, then we know, we have a variance that is not stable. It is a function of theta. It changes as theta changes. And again, this then can cause problems with respect to inference. So, of course, we don't live in a perfect world. We only have one sample to work with. We don't know what theta is, so what can we do? This is where the Bootstrap comes to the rescue. So what we can do is kind of emulate, and this is kind of the theme of what we've done a lot throughout the semester, emulate what we would like to do by taking resamples. So what we can do is this. This is the algorithm that's given in the book. take our resamples from f hat. So f hat's our regular old EDF. Calculate T star and V star. Don't worry about exactly what V is, other than that's a variance. Calculate this V star. Variance is calculated based upon a resample. And then simply plot V star versus T star and look for trends. In other words, we're just kind of replicating what we see here. Except for now we're going to have T star here, and we're going to have V star there. If we see trends, that says, okay, we have an unstable variance. If we don't see trends, great. We don't have anything to worry about. So then what do we use for V star? This is the problem. Well, if you know what the asymptotic variance is, just simply get the asymptotic variance, as we did like in project number 1, where you see the y's, replace it with y stars, and calculate it for every single resample. Then section 2.7, we learned about the non-parametric delta method. So you can calculate that for every single resample. Do the jackknife, you can do that regression method, or what you could do is use the Bootstrap. So calculate V star boot. What this means then is that for a particular resample that you had already calculated before, now you're going to need to take, let's say, M resamples from that resample and calculate then the variance. So in other words, this is a direct application of stuff that we learned about at the end of chapter 2 in terms of calculating this variance. What's new here is how we're working with that variance to figure out a variance stabilizing transformation. So, any questions so far? So this again is where then the double bootstrap comes in. So, as I said here, we want to look at possible trends. But what trends in this plot then suggest what kind of transformation we work with for T? So, going back to section 2.5. What we wanted to do was find some kind of transformation, some kind of function, h, such that the first derivative of h, evaluated at theta, times x, leads you to having an approximate normal distribution with a mean of 0 and variance that is a constant, c squared. In other words, we want this h to allow us to basically cancel out what the variance of x itself, k of theta, is. What I mean by cancel out, I mean remove theta from the line. And I showed you back in section 2.5 that what one could do is take h of theta to be the integral of c divided by the square root of k of theta. Integrate with respect to theta. Typically, it doesn't matter what c is, it's just a constant. Most people just simply think the number 1. So take h so that you get the integral of 1 over the square root of k of theta d theta. Okay, so then this leads us into discussing what are possible trends. So, example number 1. If k of theta was actually theta squared, just suppose it was, look what happens for h of theta. It ends up being the log of theta. So what does that mean for us then? If you see a quadratic trend in our plot, so if these points were scattered about maybe, just do a different plot. If they're scattered about like this, where this was theta and this was v, obviously you see a quadratic trend, so apply that same idea now to a plot of t star versus v star. If you see a quadratic trend like that, then use a log transformation. Okay. So then if it worked, just to make sure you're seeing this, if it worked, and if I were to plot the variance, sorry, I know it's hard to read, the variance of log of t star versus the log of t star, what would you expect now in that plot? Just to be something like this. So you have a way to check to see if the transformation worked. Example number 2. If k of theta is equal to theta, simply. Well, let's plug that into our integral for k of theta. And you get h of theta is equal to 2 times square root of theta. So what you do then is, again, look at for a linear trend in your plot of v star versus t star. If this linear trend exists, try a square root transformation. So, this isn't a perfect solution because obviously, in these plots here, there can be multiple interpretations of what's actually happening. But this at least gives you a tool that you can use and fall back to this little variance stabilized transformation formula to figure out what could be a particular transformation. That leads us now to an example to discuss actually applying this stuff. And I don't want to start a brand new long example. We've only 2 minutes left, so why don't we just end it there. Are there any questions? Okay, that's it for today.